years ago, a group of experimental particle physicists at Brookhaven, New York, found a new particle with a unique characteristic of strangeness -3. Their discovery was the climax of a dramatic 2-year search that had sometimes gone on right round the clock. The existence of this particle had been predicted independently by Murray Gell-Mann of Caltech and Juval, a former colonel in the Israeli army. The mysterious particle they called the omega minus, and its discovery was a significant step forward in our understanding of the ultimate structure of matter. Shortly after the omega minus was found, Horizon visited the United States and prepared a film first shown in 1964. We see the scientists responsible for the breakthrough and also one of the world's outstanding theoretical physicists, who last year won the Nobel Prize for Physics, Professor Richard Feynman.
The progress of physics seems to come in fits and starts. The really great pinnacles, the revolutionary discoveries, the great transformations of ideas come very infrequently. Perhaps in the last 200 years there's only been half a dozen such things. We might think of Newton's discovery of the laws of mechanics and gravitation, Maxwell's theory of electricity and magnetism, Einstein's theory of relativity, and in the 20th century, the theory of quantum mechanics. I think we're due for a new one. I think very soon we'll have another great transformation of ideas during which we discover the ultimate understanding of the forces between nuclear particles. Now, with every great pinnacle of discovery, there is a long preliminary process of gathering information, sorting it down a little bit, and getting it prepared to be understood. For example, for the law of gravitation, there was first the observations of the motions of the planets, then a certain amount of partial understanding, such as Copernicus's idea that the planets went around the sun, and later Kepler's discovery that they went in ellipses. But the final, ultimate law of gravitation required all this preliminary jockeying of the data around to understand it partially. In the same way, the future discovery of the laws of nuclear physics, nuclear interactions, is preceded by a partial summation of the information that's available so far. And just recently we've had one of the most important and dramatic reshufflings of our understanding, so that I think that we're almost ready to get the answer to the big question. What I want to tell you about today is this partial understanding that we've just achieved. Some time ago, things looked pretty simple. We just had theory that the atoms had on the outside electrons and on the inside nuclei, and that the nuclei were made of nothing but two particles in the world, the neutrons and the protons. And then with such a simple picture, just two nuclear particles, a nuclear problem was just to understand the simple law of force between neutron and proton. Probably some simple law, like the electrical law, that the force varies inversely as the square of the distance, or some other beautifully simple thing was all that had to be found out. So a program was launched to study the interactions of neutrons and protons, and it was discovered, as time went on, that the law looked a little more complicated ultimately, but it was extremely complicated. That it was as complicated as it could be, that the force between neutrons and protons depended upon practically everything, and it depended upon how far apart they were in a very complicated way. It depends upon which direction they're spinning, what direction they approach each other relative to the way they're spinning, and so on. In fact, it depends on everything that it can depend on, and is as complicated as it can be, except for one little thing, which I'll mention later. Now, when a thing looks complicated, it's possible that we're looking at it wrong and that we're missing some of the pieces of the puzzle. And as a matter of fact, there was direct evidence that pieces were missing in the fact that in cosmic rays, the fast particles which come from the outside somewhere, in studying cosmic rays, it was found that there were some new particles, other particles besides the neutron and proton. First, there were some mesons, which were partially expected, and then there were another group of heavier objects, one of which was called a lambda meson, and it was found to disintegrate into a proton and one of the mesons sometimes. Sometimes it disintegrates into a neutron and one of the mesons. The cosmic rays also discovered still another particle called a cascade particle, which itself disintegrates into a lambda. Now, the progress with cosmic rays was very slow and was very much speeded up by the development of modern accelerators, which produce particles as fast and as energetic as those in the cosmic rays, so that we, so to speak, have brought the thing under our own control rather than to have to wait for the odd fast particle and reaction to occur in nature. In addition, we've developed better instruments for observing the particles. Instead of cloud chambers, bubble chambers. And with these bubble chambers and modern accelerators, the progress in finding new particles has rapidly increased. 5 years ago, we were up to 30 particles. Now, we have 90 particles. So the problem has gotten a little more complicated. We used to just worry about how the things acted. Now we have to divide the problem into two parts. We have to go back a step. First have to decide what there is in the world, and then how does the stuff act. So we have to now figure out what the pattern is of available particles. In other words, what kind of a world, what the particles are that are in the world. The first thing, it turns out that they become in families. For example, the neutron and proton are very similar. They have the same mass and they have other characteristics in common. But the most remarkable characteristic is this, that although the forces between neutrons and protons are very complicated, the force between a neutron and proton and between a proton and proton are the same. That's a very mysterious accident. It's only true of the nuclear part of the force. The electrical forces, of course, are different. One is charged and one is neutral. But the nuclear part of the forces, we've discovered, has one peculiar characteristic. That is that you can change a neutron for a proton, and it doesn't make any difference to the force. We say that the nuclear forces have a symmetry. They have the symmetry that you can change neutron to proton without making any difference. The fact that we use the word symmetry here is a kind of a technical use of that word. What is a symmetrical thing? How would you define a symmetrical thing? One definition is that a symmetrical thing is something that you can do something to and it doesn't make any difference. In this book, for example, I could turn it over and it looks the same. There's something I can change something and do something to it and it still looks the same. And in this, we use the same word in the physics then to represent the fact that I can change a neutron to a proton and the nuclear forces look the same. So neutron and proton together form a family as far as nuclear forces are concerned. And it turns out that the cascade particle is a member of a family of two, one negative and one neutral. The lambda stands by itself, but there is another particle, a set of three particles that are similar, that also get exchanged and produce a family of the kind that the neutron and proton produce. Besides families, we found out that there are hierarchies between these particles. For example, lambda disintegrates into a neutron and a meson, or sometimes into a proton and a meson, and that it does very slowly. It takes a third of a billionth of a second. It sounds like that's pretty fast, but for nuclear reaction, nuclear particles, that's very slow. It should happen almost 1 billion times more rapidly if there weren't something in the way. In order to analyze this something in the way in these disintegrations, Professor Gell-Mann here at Caltech invented a method of description which describes this situation. He said that in a sense the lambda has a kind of character that has difficulty in disintegrating into a neutron and a proton, and he makes the rule that if you want to disintegrate with change of character, it should be slow, and thus is able to associate character, a kind of character to the different particles, in which he gives a numerical number. He calls this number strangeness. He says this is strangeness number 0. This is strangeness 1. You'd think actually he called it with a minus sign, but that's just an accident of history. But then it turns out that the cascade particle here can't directly disintegrate a neutron and proton. It disintegrates slowly into a lambda, and then the lambda into neutron and proton. So the cascade particle has a character number -2, being 2 steps removed in the slow disintegrations to the neutron and proton. Well, then, that is some partial analysis of the particles that are in the world. There's these families for interchange, and there are these hierarchies associated with the strangeness. The question is there any more symmetry in the system? But for instance, is it possible that an exchange of a neutron with a lambda might make no difference in nuclear forces? Or some other possible combination, that if you change a proton to a sigma and a cascade to a sigma naught or something like that in a certain particular combinations, it makes no difference. People have tried very many attempts to find such additional symmetries. In order to help them, they've used the mathematics of what's called group theory. Group theory is just nothing but the mathematicians have analyzed a lot the problem of what happens if you exchange one thing with another and then something with something else, what are the net result of all that, so that the mathematicians have prepared for the physicists the necessary mathematics called group theory to analyze this. At any rate, many types of possible systems of exchanges have been suggested to understand the way the world works, and in each case sometimes you would predict something that wasn't exactly in accord with experiment, and it didn't look very hopeful. As a matter of fact, I myself, after playing around with Gell-Mann, trying together, we tried many combinations, came to the conclusion there probably wasn't any other symmetry in the system. The problem is very hard. Why should it be hard? If a thing is symmetrical, ordinarily, with one glance of the eye, you could see immediately that it's symmetrical. So why is it that it's not possible to look right away at the character of the particles that are discovered and see the symmetry? There are two reasons. First, the symmetry is not perfect. In the case of the pattern that you can replace neutron by proton, that is very accurate, but it is not exactly perfect in nature because the two protons interact electrically while the neutrons don't. But if we leave out the electricity, it's quite perfect. The electricity is only 1% or so. However, we know already, because the masses of these particles are so different, that any other symmetry that must be there must be quite a bit off, by 10 or 20%. To look for a somewhat symmetrical thing takes more skill than to notice a symmetrical thing. The other part of the problem is that we have missing parts. If you had a vase which you knew was nearly symmetrical and half of it was broken off, or nearly half of it was broken off, it would be a little bit hard to tell the pattern of symmetry. So that when there's only a limited number of particles, it gets somewhat difficult. For example, there was known a set of 4 particles in addition to this set, which belong together in the kind of family that these belong. Then it became clear that there was another set of 3 more that were similar for such exchanges, and it was part of a suggestion. There was a suggestion made by Gell-Mann and independently by Professor Feynman of a certain particular pattern of interchanges among all these particles which would permit an understanding of what was known so far, but would only permit these 4, provided these 3 and another pair and still a third particle, all by itself, existed in the world. They, when they made this up, only knew about this and a little bit about that, and were very reluctant to suggest that it was true because there were so many missing pieces it was unbelievable. However, when these particles turned out to exist and to fit their triangle of interconnections, which they expected would occur, they became more ambitious and suggested that in fact the theory is right. In order to make this theory right, however, this particle here was missing. Now, many of the other symmetry systems predicted new particles, and many new particles were found. But in the confusion, the particles had no particular special properties, and one could make an accident. That is, nature did have a particle something like what you were looking for. But this new particle that was predicted by the Gell-Mann theory was very peculiar. It had strangeness -3. And this theory predicted that they should, with strangeness -3, which means that it would only be able to disintegrate in 3 steps before it got to neutron and proton. This was so unique and definite a prediction that the theory would be made and broken very easily by experiment. So the very interesting question was, do they have the right pattern? Is there an extension, an additional symmetry among the particles, an additional fact to simplify our understanding, by which the families of 2, 3, and so on can be combined into one element, 2 elements, and thus take our 90 particles and replace them by 2, 3, or 4 groups? If so, of course, we're making enormous progress. And the big question was, experimentally, does this omega minus exist or not? This was a moment that's characteristic of physics, that's one of the big thrills and mysteries. How is it possible, by looking at a piece of nature, to guess how another part must look where you've never been before? How is it? It's only in modern times that man has really been able to guess what nature is going to do in situations that he's never looked at before. And here's an example of it. With many strange particles, by looking at those which you've seen already, it is possible to guess that there must be something that you haven't looked at yet. The reason this is possible is partly man's ingenuity, but obviously more important is nature's inner simplicity. To look for this particle is a typical, dramatic scientific investigation.